many of the standard prescribed physics textbooks start with units and dimensions as a very short, very boring, very neglected chapter which you quickly get through, right? I've always found dimensional analysis very interesting because it appears to give you something for nothing, right? You can do a little dimensional analysis and convince yourself that the period of the pendulum is proportional to square root of L by G, much less work than actually doing the derivation. Units, honestly, when I started the study of physics, units was something very simple. The day was divided into 86,400 seconds. We all knew what a day was. And there was one piece of metal in Paris which defined a kilogram, and another piece of metal in Paris which defined a meter. Now, things have completely changed, right? So in 2019, strange things happened. The velocity of light was declared to be a certain number. So you can no longer measure it, okay? It's, I think, 299, okay, I've forgotten, but maybe 452,798 or something like that, meters per second. Okay, that I had kind of got used to earlier. The second was defined now in terms of a particular transition or special frequency associated with the cesium atom. Okay? Again, there's one nice number which looks like a mobile number, 9192631770. Periods of this oscillation is 1 second. But the strangest thing is the way that the kilogram was defined. Okay? That piece of metal in Paris was sort of demoted. It's still there. And the kilogram was defined indirectly by defining Planck's constant. So Planck's constant again is now a given number. I've forgotten. I think it starts with 6.626 and then keeps going. Okay. So I thought there's something interesting here. I read it up myself because I didn't fully appreciate what was going on. I thought I'll convey that to you first. So maybe in the first half, we'll talk of the strange way these units have evolved. And then, of course, right. So physics is all about measurements and fitting those measurements to some theories. And the theories produce numbers and the measurements also produce numbers. But these numbers are always in some system of units, okay? Except numbers like pi, right? Which is the ratio of two lengths, and therefore it doesn't have any units, or it's dimensionless. So the physical quantity is a number times the unit, and I'm just using the square bracket to talk of the unit of that quantity, okay? And traditionally you have length, mass, time, and if you are going to do some electrical things, you should have a unit of charge as well, Coulomb, okay? So the unit of any quantity can be expressed in terms of the units of length, mass, and time, and if charge is relevant, charge. So let's take one interesting statistic is that a masala dosa is about 1 megajoule, 1 million joules. Let's concentrate on the joule part, right? It's a unit of energy. And for that, the power of length, which I have denoted by a little l, would be a what? What's the power of length in the unit of energy? 2, right? Right? Time is -2, right? And m is 1. And charge? No charge for the masala dosa. Okay. So these numbers, LT, MC, are called the dimensions of this physical quantity. I'm sorry, I'm just going over standard definitions which you all know. Then there's this useful principle that an equation should have the same dimensions on both sides. So that's how you got the shortcut to square root of L by G. You said the period is the dimensions of time. And then you took the length, and you took G, and you even threw in the mass of the bob. Okay, I don't know any physics, so maybe it depends on the mass of the bob. And then by some miracle, the mass got a dimension of 0, and L and G got dimensions of half and minus half, right? But I'd like to give you an equation which is dimensionally incorrect, but still useful, okay? And also tell you how to make it dimensionally correct. So you go and eat in a restaurant, right? You have a bill, and then you have a tip, right? Now, some places just say give a 10% tip. Maybe that's a reasonable thing to do. But you know, restaurants come in a huge range, especially in Bangalore. I mean, you can get that masala dosa for 70, you can probably also get it for 700, I mean, in some other places in Bangalore. So would you feel comfortable giving a 70 rupee tip just because you ate a 700 rupee masala dosa? So in general, okay, you go to a fancy place, it's got a nice atmosphere and so on, but still to scale it proportional to the bill, somehow I was reluctant. So I came up with this formula. Tip is equal to square root of bill, okay? So, you know, if someone gives you something for 1 rupee, surely he deserves a 1 rupee tip. I mean, come on. 100 gives a reasonable number, 10%. If it's a 1,000 rupee bill, I mean, if you don't feel like giving 100, maybe you give 31.6 ... rupees, right? Actually, but you can clearly see that this formula is not true in all systems of units. So let's consider a bill which is some 84 rupees, okay? So you convert it first to dollars. So it's $1. And then are you going to give a $1 tip to that according to this formula? No. So the correct, if you want to make this formula correct, you should say tip by the rupee is the square root of bill divided by the rupee. So now both are dimensionless, okay? And now you can, even if you travel to US or something, you can still use this formula. Of course, in the US, they would throw you out if you give such a small tip, but that's a different matter. Astrophysicists are very fond of writing all their formulae in this form, right? So, for example, I could say the period of a planet divided by the year squared is the semi-major axis of the planet divided by 1 astronomical unit. That's the distance between the Earth and Sun, cubed. We know that T square is proportional to A cubed. And I've just picked these numbers so that the formula works for the Earth. And now it'll work for example, if you put this number equal to 30, which planet goes around in 30 years? Must be a very slow planet. What is slow in many Indian? Shani, right? Okay. So that's just a small remark on this. The shortcut bit I've already talked about, but you should worry about it a little bit. Now, I would like to sort of criticize this derivation a little bit. First of all, of course, it doesn't give you the 2 pi, so it's not useful for actual predictions. Then you've already built in the answer by using this quantity little g, okay? Now, what is little g? I mean, before Galileo, people didn't have little g, right? He was the big G who gave you little g, Galileo, right? And how did he decide that there is something called acceleration due to gravity? By dropping bodies of different masses. I mean, at least so the legend says. So he'd already checked independence of mass when he defined little g. So the fact that this derivation gave you independence of mass is sort of built in by using little g. Anyway, that's just a small side. But now, I mean, this is just a kind of warm-up. I'd like to go back, a little back into history. So let's look at the unit of length. And after all, little more than 75 years ago, we were ruled by the British. So let's take a unit of length which was given to us by the British, namely the yard. Now, you may say we are all metric, but I don't know, I've never heard of a 5-meter sari. It's usually a 6-yarder, right? Of course, 5 meters is not 6 yards. I mean, they'd be cheating you slightly if they gave you 5 meters instead of 6 yards. The cricket pitch is 22 yards. And if you go to a remote village in Karnataka and ask some gentleman what the distance is to the next village, it's a yard furlong, sir. Furlong is 220 yards. So the yard is not dead, even here, okay? So what's the origin? So I just looked it up, right? Apparently it comes from this word, it surprised me, which is gird. So what does gird mean? Yeah, you can, Sam went through a gesture. You know, if you're getting ready for a fight, you gird your loins. I think the Hindi idiom is very nice, kamar kasna, same thing. So this distance became the yard, okay? Now, apparently that's how it started. So that would be very useful, right? If I was a cloth merchant, I would, when I was buying cloth from someone, I'd buy it after a meal, so I get more cloth, yards, and then when I'm selling it to someone, I'll sell it, you know, on an empty stomach. So clearly, that's not right. And in fact, proper units, it goes back to the year 1100 or something in UK, where I read up the history, precisely because people were worried of cloth merchants cheating you or something like that, okay? So then they came up with this interesting idea. We are going to define the yard as the distance between the tip of the nose and the outstretched arm of Henry I, right? Now, it's fine. It's I mean, even today, that's fundamentally no different from taking a platinum piece, right? Except it's Henry I. But there are some practical difficulties. You can't take Henry I to each and every cloth shop, right? So what do? You create some secondary standards, right? Could be pieces of string. Then gradually they realized that string can be stretched a little bit and so on. So they went for pieces of wood, and then even wood deforms, so steel. So, you know, after a couple of centuries, there were lots of these steel rods floating around, which were all called the yard. Now, you would want consistency, so you would want to compare these with each other. But what tells you that this steel rod is actually better than this Henry I? I mean, how do you know? Because, so what you could do is, you could keep going back and measuring Henry I with your steel rod. And let's say, sometimes his arm went a little beyond, sometimes his arm went a little less. What's the conclusion? Either the problem is with the steel rod or with Henry I. Right? I mean, look, being human, you know, his muscles might contract, something could happen. So how do you decide that? Remember, you don't have any independent standard of length, okay? So what you can do is you can compare these rods with each other. And if they show consistency, then you can probably conclude that, you know, Henry I is getting on in years and maybe he's shrinking a little bit or something like that. So that was fine. But then people started comparing these rods with each other. So even any secondary standard has to have a consistency, okay? So they use steel. Meanwhile, across the narrow thing, right? Okay, they could compare them with each other, and there were some inconsistencies at some level, probably good enough for buying and selling cloth, okay? Meanwhile, the French, separated only by a very short stretch of water, had taken a much more scientific approach to this whole problem. So they tried to define the meter, okay? So let's see how they went about. But it's interesting that the English, and therefore the UK, who also follow the English, US, who also follow the English, didn't give up the yard as an independent unit until 1959, okay? Finally, they agreed that the French have done it better, so we will define the yard as 0.9144 meters, okay? So the meter is now, the French said, no, none of this Henry I business. So we will use the Earth, okay, as a standard. So take the distance from the pole to the equator, measured along a line of longitude, and take 1/10 millionth of that. So that's useful to know that the circumference of the Earth is very close to 40,000 kilometers or 40 million meters, okay? So 1/4 of that. So that was fine. Except, I mean, if the Earth had been, first shock they got was that the Earth was not spherical. And this was the period where there was this, I think Sam mentioned this also, right? That the French initially were not very receptive to Newton's ideas. Newton had predicted that the Earth would be slightly flattened because of the rotating, centrifugal force and all that. But the French said, no, we are going to measure it. So they measured, and one person said it was oblate, and another person said it was prolate. So they sent one expedition to Peru, one to Norway, and so on. Finally, they got it right. Unfortunately, when they started measuring better and better, they realized that the different arcs connecting the pole to the equator were slightly different. So if you wanted a really good standard of length, you would have to give up that. Okay? That means the Earth is not even perfectly a flattened spheroid, and it's got some other deformation. Okay? Then another thought, take a pendulum, right? You have a unit of time, perfectly good unit of time, the second. So keep adjusting the length of the pendulum until the period is actually 2 seconds, 1/2 period. So you will find that they could tie the meter to the length of the seconds pendulum. Unfortunately, the value of G keeps varying from place to place. Okay? So that was again not good enough. So finally, they went for this platinum bar, whereas the English went for steel. But interestingly, the bars were all made in England by a company called Johnson Matthey, because they probably had the monopoly over mining the platinum in South Africa or something like that. Okay? So look at the history. And they have given the uncertainty also. So you can see it's coming down, right? And as I said, in 1959, the British agreed to accept the meter, that platinum rod, and in 1960, the whole world gave up the platinum rod. Okay? Now, why was that? So, of course, copies of this rod existed, but then people realized that, you know, we should do something which can be independently done in every country. Okay? So, great opticians like Michelson, Fabry, Benoit, and so on, I don't think I have their names here, they were commissioned to come to this sacred place in Paris. Of course, temperature had to be controlled, all that. And there were 2 scratches on the rod. And then they would align their optical mirrors and see how many wavelengths of light fit into that. It's not one of your experiments, but I think the equipment to show these, how many wavelengths fit into between 2 mirrors is definitely there in the lab. You can request Iqbal to set it up. It's called an interferometer. Okay? Now, what happened was that people, then of course you wanted a light source whose wavelength was very well defined. Now, if you just take some chemical element, it'll have different isotopes, it'll have slightly different wavelengths. So and also if the atom is very light, then at a given temperature, it'll move around with some velocity because of temperature. So they picked this krypton, which is pretty heavy, and they picked one isotope, 86, and they standardized it. So now they could define the meter to, 0.01 micrometer. So that's pretty good, right? And there it remained till 1983. Now, suppose you took this definition of the meter, then if you wanted to set up the meter in India, you just got a Krypton 86 lamp and you could do it independently. Then the same thing that was done in England long ago, compare the consistency of different people doing the same experiment. It will never give exactly the same value, right? And some of the uncertainty, well, you could say, it's not this guy's experimental skill, but even with good experiments, there's always going to be some scatter, some variation, okay? So that means the standard is precise only to that level. So this Krypton, again, they've given you the number. It was okay at 10 - 8 level. Meanwhile, as we will see shortly, the standard of time was enormously better. So if you take someone measures the speed of light, and he measures the length by means of this Krypton 86, but he measures the time by means of, we'll see, a cesium clock or something like that. The error will entirely be dominated by the length measurement, okay? So then people had the bright idea saying, look, since the time measurement is so accurate, let's forget this Krypton 86. Let us say the speed of light is 299,758 or whatever, right? And let that define the meter. Okay? So that's how the speed of light became a fixed number. Right? I remember reading about it in 1983 in this journal Nature, where the editor sort of humorously said that this is the last chance for anyone to measure the speed of light. Of course, that doesn't mean those experiments are useless, but now they should be considered as experiments to realize the meter in that laboratory. In fact, if you go back to our very first equation, which said a physical quantity is a number into a unit, right? You could either think of it as defining the physical quantity, or you could also think of it as defining the unit. If you fix the number, then the unit gets defined, right? Provided the speed of light is not something which is going to change. And there, of course, we appeal to Einstein, right? You're not supposed to mess around with the speed of light, okay? So that's how the unit of length came to be defined in terms of the unit of time and a given number for the speed of light. Now, of course, they didn't pick an arbitrary number. They picked the best number that people had got with the then uncertainty of length. So mean solar day, MSD is not the person you think it is. It's the mean solar day, okay? Because the length of day varies, of course, because the Earth is sometimes closer to the sun and sometimes further away from the sun. So therefore, the angle through which it has to turn to face the sun again is slightly different, okay? So you take the average and take 86,400 seconds. And this was there for a very long time. Of course, day is a big unit. You wanted fractions. And in historical times, people had clocks based on, of course, sundial was always there. But at night, maybe you burnt a candle, you had water dripping of something. But then the pendulum came along, okay? And that improved things greatly, but not perfect, right? But it also turned out to be very important for strategic reasons. If you were sailing and you didn't have any other source of information as to where you were, you could look at the pole star or some other star and see where you were with respect to the North Pole, right? So you would know your latitude, but you wouldn't know your longitude. For that, today, the easiest way to find out your longitude is, watch a tennis match in Australia, right? Look at that clock and look at your clock. Right? The difference will tell you what the longitude difference is, right? At the rate of, 15 degrees per hour or something like that. But in those days, before they had TV and tennis matches and all that, you had to set your clock, say in London, if you were a British seafarer, and then carry it with you, so it'll keep showing London time. And then the local time you can find from the sun and so on. And by comparing those two, you knew your longitude. And if you knew your longitude, you had a good navy, you could beat the other guys, you could loot their ships and become rich, okay? So there was a big prize, and a person called Harrison made the big killer was thermal expansion. So he came up with some clever scheme to contradict thermal expansion. And it's quite an achievement to reach 1 second in 100 days, okay? 10 minus 7. So keeping time in this way, with these pendulum clocks, astronomers observed the planets, and then they could check Newton's laws, right? Unfortunately, Newton's laws were not working. So when they saw the moon and they predicted where it was going to be, the moon always seemed to be going a little bit ahead of that. It's called the acceleration of the moon, okay? And they started getting worried. I mean, is there something wrong with Newton's laws? It turned out that nothing was wrong with Newton's laws, but the t in Newton's laws was not the same as the t that they were measuring, because the t they were measuring was tied to the rotation of the Earth. And there was independent evidence, very interesting evidence, that the rotation of the Earth is slowing down. So you might have noticed that, especially during this summer school, you will notice the days will keep getting longer and longer, okay? But in reality, the length of the day increases by some 2 milliseconds every century. Seems a very small effect, but it's a cumulative effect. So why a lot of evidence comes to this. One is, of course, you should have a clock better than the Earth. And the moment atomic clocks came along, you had a clock better than the Earth and you could directly check. You could measure time by the rising and setting of stars, which is tied to the rotation of the Earth. Or you could measure time with your atomic clock, and you could see that the Earth was, by and large, slowing down. By the way, suddenly, sometimes it speeds up also for reasons which have to do with things happening inside the Earth. Okay, so let's leave the geophysics aside for a moment. Okay. But the other fascinating evidence is that you could calculate eclipses. And the Babylonians, amazing people who wrote on these clay tablets, and we can still read them if you know your Babylonian, you can read them after 4,000 years. They recorded eclipses. So number one, the dates of certain kings are known absolutely precisely. In the reign of king so-and-so, such and such an eclipse happened, which was seen from here at 3 in the afternoon. So everything was fine except the 3 in the afternoon. According to calculations, if you see, the eclipse has nothing to do with the rotation of the Earth. It's only the alignment, right? But where the eclipse will be seen in the sky depends on the rotation of the Earth. And this is one of the strongest pieces of evidence. The 4,000-year-old eclipse, this small effect of 2 milliseconds per century, you can work it out, will accumulate to several hours. Okay? So anyway, the Earth is not a good clock. So then in 1956, people said, let's use the orbit of the Earth around the sun. That's slightly better. So it's a useful fact to remember that the Earth takes 31,556,925.9747 seconds to go around the sun. And that was fixed as the standard of time because the atomic clocks had not yet come in. Okay, so this had a slightly better accuracy. But you see 10 minus 11 is already getting way better than the meter. Okay? But when the atomic clocks came along, they started beating it. So the cesium clock, for example, the initial cesium clocks had an accuracy of 10 minus 13. So what that means is that if you take a year as having 3 times 10 raised to 7 seconds, and you multiply that by 10 minus 13, you get 3 times 10 minus 6 seconds. Hey, by the way, these slides will be freely available. Huh? So relax, sit back. Right? So that's some microseconds, okay? But actually microseconds is not good enough. Not good enough for what? Not even good enough to take you to your favorite pizza place using Google Maps, okay? So how does this thing work, this GPS? I mean, let's not get into the details, but basically there are these satellites whizzing around. They all carry the cesium clock. Of course, the satellite model cesium clock is not the best cesium clock, but there are some really good cesium clocks owned by the US Navy, and they are more accurate because you can put a lot of equipment in a big room, and they keep correcting these satellite clocks, okay? And then signals come from you need 4 signals from 4 satellites. And just to provoke you, I'll say you need 4 satellites because space-time is 4-dimensional. Or a simpler way of thinking about it is that using these 4 numbers, your mobile phone solves for your 3 coordinates with respect to the center of the Earth and the local time. So you don't need an atomic clock in your mobile, okay? In fact, this corrects the clock in your mobile, all right? Now, if you want to, you're going to a wedding and you don't want to attend the wrong wedding in the neighboring thing, you need an accuracy of few meters, okay? And therefore, light travels, so you need something like 10 minus 8 seconds, right? Of course, these are corrected every few months. So this GPS is based on cesium clocks. And actually, the cesium clocks have got better and better. So right now, they are at the 10 minus 16 level. That's very impressive. I think that's more like some nanoseconds, 10 minus 9 seconds in a year. Okay? So the accuracy is now measured in feet. So the time as distributed all over the world, and it's important not just for physics or astronomy, but even for the stock market, because people nowadays, will buy a share and sell it a few milliseconds later and try and make some profit. I mean, I couldn't believe it, but people assure me that is true, that's happening. So then you better be sure that, just like the old cloth, people worried about the standard so that they wouldn't get cheated. Now the stock market people worry that the clock should work perfectly because otherwise, they might make some gain or loss. So that is the standard of time today, but that is not the best clock. Okay, the best clock, the record is set by something called an optical lattice clock. The simplest way of understanding the optical lattice clock is to ask your future speaker, Sanjukta Roy, who works in that field. So I will keep completely silent about how this works, okay? But its accuracy is 10 minus 18. Now that is scary. The way they state it is, it will gain or lose 1 second in the age of the universe, okay? Why we would want that accuracy, I don't know, but once you get physicists onto a problem, they keep getting better and better. It's based on lasers and ultimately based on the vibrations on atomic transitions. I mean, that's you have this equation E is equal to h nu. So if you have well-defined energy, you can have a well-defined frequency and you can have a well-defined scale of time. That's the idea of this optical lattice clock. So in case you are going to buy one and put it on your wrist, this is what it looks like. Okay. So I would not encourage you to do that. Okay. So I've kept for the last of the units part, the strangest one, at least in my mind. Oh, okay, what did I do? The kilogram. Now, actually, standard weights were found. Even the Indus Valley has standard weights. And even historians see that if the weights in one side are similar to the weights in the other side, it means these two guys are probably trading with each other, or they were at least not cheating each other. And so, for quite a long time, there was this platinum iridium mass kept in Paris, but it was found to be unreliable. And the reason is kind of interesting. This is what it looks like. So, of course, again, the same problem with Henry I. You can't carry this all the way. It's kept highly protected. There are 3 keys to access it. Temperature controlled, vacuum, all that kind of thing. So copies were made and sent to various, I think India also got copy number 57 or something. But then, same story repeats. People compare these copies. And now and then they take that copy to Paris and compare to the original. So look at this graph, okay? In 1889, they all agreed, okay? Now the difference is small, it's micrograms. So you don't have to worry about buying your vegetables in Paris or anything like that. You'll get your fair deal, apart from a few micrograms. But look at these, don't agree with each other. And this is one of the unsolved problems in physics. So even after gravity is quantized, people may not know why these things. It could be many reasons. Maybe the platinum is supposed to be chemically inert, but maybe some molecules stick to it. It has to be polished and cleaned. So people have gone into, they have studied solvents, they have studied pollution in each place. So this was unexplained. So finally people said enough is enough, okay? We can't be relying on this thing, which is, of course, see, it's not bad, no? I mean, but it's, I think 10 minus 7, right, is what I gave. But look at the other thing. Time is 10 minus 16, and mass is 10 minus 7. So that's really bad, right? So people said, we will tie the kilogram to Planck's constant, okay, which is as sacred as the speed of light. Now, dimensionally, that is possible, because Planck's constant is m, L squared, t minus 1. So if I have a unit, let's say I have a good unit for L and a good unit for T, because I've just told you they're pretty good. Then you do whatever you need to do to measure Planck's constant, okay? And you will get a number, but the number will fluctuate because your kilogram is not, you might be using your idea of the kilogram in your measurement and I might be using mine, okay? So that's not good. So the best thing is to kick out the kilogram, fix the value of Planck's constant, and use that to define the kilogram, okay? I mean, in principle, it's no different from kicking out Henry I and moving to a piece of string, okay? Because you think the string is more stable, okay? So this has actually happened, okay? So if you, I don't know, just a little survey. If you were inflicted with a chapter on units, either in your secondary school or in your first year, what statement did they make about the unit of mass? Did the book make? Did they tell you about this 2019 revolution, or did they say it's a lump of platinum in Paris, or they just kept quiet about it? Platinum. So now you know better. So now that platinum could be removed and lots of expensive jewelry could be made from it, I suppose, looking at the ads in the papers. But it's still kept in a museum. There's a museum there. Now, this is going to be a little complicated story. Huh? How do you connect the mass to Planck's constant? Okay. So, in physics, there are effects, like Raman effect, so you become famous. Hall effect, we will encounter, Compton effect, and so on. So there are two effects which we have to understand. And I promise you that after my explanation, you will not understand them fully, because honestly, I don't think I understand them in full depth. I read them for this lecture and I'd heard about them earlier. They are both, of course, quantum effects, because you have to bring in Planck's constant. So one is called a Josephson effect, 1962. The other should be called a Klitzing effect, but it doesn't sound so nice. So it's called integer quantum Hall effect. Don't worry, I'll tell you what it all is, or try to. And in between, there's this beautiful piece of apparatus called the Kibble balance. There is a slightly modified version of that, which is one of your 4 experiments. So that's one reason why I chose to expand this story a little bit. Now, this Kibble balance started as something else called the Ampere balance. So again, does anyone remember the definition of Ampere? The old definition, which is also the one I was taught. I think it is that current which, when flowing for 1 second in 2 parallel wires separated by 1 meter, gives them a mutual force per unit length of twice 10 minus 7 or 1 newtons, okay? So that's the old. So let's say, all right. So there is a force, and the reason is that each wire produces a magnetic field, and that exerts a cross product of that I and B, gives you a force, okay? So in principle, you could weigh a body by, this is called the Ampere balance. You have a coil, and okay, you could have, say, a magnet like this. So its field lines would spread out. So you can see that if there is a radial component of the field and the current is flowing like this, you could get forces up or down. And believe me, when you do the experiment, you will get it either up or down depending on how you connect it. Okay, at least that's what I saw in the video. So Kibble was given the job of improving the Ampere balance. So I've written the formula. You have the current, cross product with the magnetic field, and the total length of the coil. But at some point, he had this brilliant idea saying, obviously the inaccuracy here is going to be in measuring B and L, okay? So he said, with the same setup, I'm going to do something else. I'm going to move this coil, okay? And then the Faraday's law comes in. You have some changing magnetic flux, okay? And that will induce a voltage, okay? So this B and L can be cancelled by first weighing the body and passing some current to cancel the gravitational force. Of course, it's really weighing, it's not the mass. So someone else has to give you G, but what is G? G dimensionally is LT to the minus 2. And we've got a brilliant unit for L and a brilliant unit for T, right? So basically, in a vacuum, they drop a corner reflector, send a laser up and down, drops, measure the number of wavelengths, etc., compare it to a CCM clock. I mean, easier said than done, but you can get a fantastic value of G, which will not spoil the accuracy. But cancelling B and L was fantastic because then you get a voltage. Of course, this is going to transfer the problem. So to get a good idea of your mass, you should have a good standard for I and a good standard for V, okay, for the voltage. So, quite simply, Josephson told you, he gave you a value of V, which depends only on your unit of time and the fundamental constants. And Klitzing did one better, the quantized Hall effect. He gave you a resistance which contains only the fundamental constants. Okay? Now that sounds like a lot to swallow. And as I said, I'm not sure I'll do justice to it, but it makes a nice story. So here is Josephson. He looks absurdly young because he was absurdly young when he proposed this effect. And as a digression, I could tell you, superconductivity was not understood for a long time. Then in 1956, a fairly young man called Cooper said, that's because you've been thinking of single electrons, but he did a simple calculation which showed that electrons can pair up. No one believed him, except two other people called Badin and Schrieffer. So they got together, and based on this notion that electrons function as pairs, and these pairs behave like Bose particles, and they can all be in the same state, okay? They gave a very successful theory of superconductivity. This is 1958. However, the person who by the 1960s, who is supposed to have the deepest understanding of superconductivity, is an American physicist called Philip Anderson, who passed away recently, okay? Or maybe his centenary was recently, he passed away a little before that. So he had the deepest understanding of superconductivity, including, you know, the original BCS theory had some technical aspects which were not well understood, and he clarified it. So then he went and lectured in Cambridge, right? So here's the man who understands superconductivity the best. And then this student says, but what does this phase mean? He had a complex number which describes the ordering in a superconductor. He said, what does the phase mean? Can it be measured? Anderson says, I don't know. So next morning, Josephson says, this is how you can measure it, okay? So it's one of the great stories in physics. So this is the equation. I mean, Josephson has 3 or 4 effects. So I'm just telling you the one that we are interested in. So the experimental setup is a junction between 2 superconductors separated by something which is not superconducting, okay? Then you apply, well, there are 2 effects. One is you can apply a voltage difference to that. And if you multiply that voltage difference by twice the electron charge, because now remember, electrons are moving in pairs, that will give you the kind of energy needed to transfer one pair from one side to the other side. So it's no big surprise if it emits radiation of frequency nu. Except that everyone would have thought this is a very approximate relationship. After all, the initial energy may not be exactly V, right? Could be something else. But that's where the beauty of all the electrons behaving in the same way comes in. And this is an exact relation. So this could be used as a way of generating a frequency nu given a voltage. But I already told you that frequency nu can be measured with fantastic accuracy based on the cesium and later descendants of that. So really this provides you a standard of voltage. Okay? Well, strictly speaking, of electron charge times voltage. Now, but the other effect which he predicted is that if you shine radiation with a frequency nu on this junction, it will develop this voltage. It's a bit like a solar cell, but again, that's very crude, right? A solar cell, you send in a photon of some frequency, h nu, and it will develop a voltage V, which is of the order of h nu. But those are all very approximate relations. The greatness of the Josephson effect is, as far as we know, it's an exact relation, which has to do with the mysterious property of superconductivity, of all the electrons behaving in this very ordered fashion, okay? So, this is one device now, a Josephson junction. You shine microwaves on it, and the frequency of the microwave you know from your cesium clock or anything like that. Therefore, you have a standard of voltage. So today, you can buy an array of large number of Josephson junctions connected in series, and it will give you exactly this much voltage to some 10 minus 8, 9 accuracy, or whatever accuracy your microwave is, okay? Oh, okay. Yeah, so that's the effect. Now, here is Klitzing. Any guesses as to what is that object he's holding in his right hand? Yeah, it says Nobel Prize. Seems very happy. Josephson doesn't seem that happy, I mean. But now, I'm going to take it in slow stages. Okay. So, there is a quantity called RK, K for Klitzing. Dimensionally, it is resistance. Okay. Which means it's a ratio of a voltage in some experimental setup to the current in the same experimental setup. I'll tell you what voltage and what current in a minute. Okay. And earlier, some physicists had given some argument that in a very special situation where a semiconductor, where all the electrons were confined to the surface, in a strong magnetic field, at a very low temperature, this resistance might have the value H over E squared. So at least let us check that H over E squared has the dimensions of resistance, okay? So energy into time by charge into charge. So this is a current in the denominator, right? Charge divided by time. And the product of charge and voltage is energy, right? So if I cancel these, this becomes the voltage in the numerator. So H over E squared has the dimensions of resistance. It has the interesting value of 25,812 point ... ohms. But why on earth should any object have that resistance correct to 9 decimal places? That's, well, an honest description of both these effects can be given maybe at the end of a second course in condensed matter physics. Okay, so therefore, whatever I'm going to tell you, please don't take very seriously. Okay. Yeah. So let's look at this. This is the so-called Hall setup. Hall effect is from late 19th century or something. So Mr. Hall took some wire or actually a kind of bigger than a wire, put a magnetic field, sent a current in one direction, and had the brilliant idea of measuring the voltage in the perpendicular direction. But he knew why he was doing it. Right? So you're sending a current like this. So some charge is moving this way with some velocity. But the moment you put a magnetic field, there's going to be a force V times B in a perpendicular direction. Right? V cross B, if you like. So then maybe the charges will start moving off like that. But you're not given any connection between these two. Your connection is between these two. Right? So charge will simply accumulate here and deplete here till some electric field develops which cancels. That voltage you can measure. Of course, when you measure voltage, you should not draw current. I mean, that you know. Right? Voltmeters are supposed to have very high resistance and all that. So this is called the Hall voltage. So the ratio of the Hall voltage to the longitudinal current. Or maybe we should call one of them X and one of them Y. I think that's what I've done in my figure. Okay. So whatever I'm giving you here is just a textbook description of Hall effect. So the Hall voltage is the Hall electric field into the width, right? Now the electric field is supposed to cancel the Lorentz force, which is V times B. Okay? So this is also V times B times W. Okay? Now, now if you want to know what the current is, the current in the Y direction, this is number per unit area, right? Electron charge, velocity. So velocity is distance traveled in a unit time. So if I take a unit length in this direction and I wait for 1 second, I'll have a rectangle of dimension 1 into V or V delta T, if you like. And if I multiply that by number per unit area, this is what I'll get. That was for 1 centimeter, so multiply by width. So I'm using this equation to substitute for V times B times W, which happens to be B by NE times IY. So this Hall resistance, Hall voltage divided by current is just B divided by NE. So it's very useful if you to find out how many carriers there are per unit area, or if you know that to measure the magnetic field. See, if you have wires carrying huge amount of current, you don't want to cut it and connect it to your ammeter. So the traditional method is to use something called a Hall probe. You take that Hall probe near this wire. Even in my days in GMRT, I used to see our electrical engineers doing that. Okay. So Hall resistance is B by NE. So far, so good. Where is Planck's constant, right? Now, for that, you have to go to low temperature and all that, and then let's see what happens. So electrons start moving in circles when you put them in a very strong magnetic field. And what's the force toward the center? E times V times B. And I used to be taught two formulae for centrifugal force, V squared by R and omega squared R. But there's a third formula which is convenient for us, which is V times omega, okay? So the frequency straight away comes out as EB by M. It's called the cyclotron frequency. So it's a simple classical result. Now, you can do what Mr. Bohr did. You can say the angular momentum is m r squared omega, which is, right? And omega I have substituted now, EB by m, so m goes away. So r squared into EB, and put it equal to some integer times h. And that integer will label the levels of this electron in the magnetic field, okay? Let's take the integer to be 1. So that tells you what is r squared, right? It's Planck's constant divided by EB. Now, what has this got to do with our earlier calculation of Hall? Now we'll bring in one more great of quantum mechanics. We'll bring in Pauli. What's the maximum number of electrons you can pack, right? If each occupies an area r squared, then the number of electrons per unit area would be 1 over r squared, right? Because you are packing these circular orbits. By the way, any of the experienced physicists in this audience will tell you that I'm cheating you. So I'm also telling you I'm cheating you. But this is not wrong, but it has to be improved, okay? So now for n, you just substitute 1 by r squared, okay? Then the magnetic field goes away, right? I have some exclamation marks here because they're anticipating what's going to happen, right? Simply becomes h over e squared. So here are all the warnings. So as I said, Klitzing himself was surprised when he got exactly this number. Now some Japanese physicist called Ando had calculated more or less what I showed you. He said, okay, but he said, look, we are neglecting so many things, so maybe you will get approximately h by e squared, who knows? But so this gentleman decided, let's see how good it is. And he was shocked. So the real reason why, in spite of all these imperfections and so on, you get this exact value is subtle. I mean, let me just leave it at that. It's a way of. So now we have a standard of voltage, a standard of resistance. So that gives you a standard of current. And therefore, you can weigh an object to this Kibble balance because that involved the product of voltage and current, if you remember, right? Okay. Now, while all this was happening, there was another bunch of people who were trying to get at the kilogram by other methods, okay? I find that also very interesting. So you take silicon, which is one of the materials which can really be purified. That's why it's chosen for the semiconductor industry. So you make a sphere. And by the way, this one is made by hand. So even in this 21st century, apparently these perfect silicon spheres, I mean, they have to be perfect to the kind of accuracy you're looking for, 10 minus 8, 10 minus 9, like that. But you can measure the diameter with optical interferometry and so on. You don't want to mess around with different isotopes. So someone has to purify the isotopes for you, okay? I think the German people who did this first got the purified isotopes from Russia, so probably before. Then you can measure the atomic separation by X-rays. Many of you may know that atomic structure is probed by X-rays, but this is a very special X-ray measurement, okay? So then if you know the diameter and you know the separation of atoms and you know the crystal is perfect, you know the arrangement, you think there are no defects, then you can count the atoms, right? So now the mass of this gets connected directly to the mass of the silicon-28 nucleus. Right? And this is something which in principle can happen independently in every country if you're good enough experimental physicist, or you buy your silicon sphere for $3 million, which is actually quite cheap if you think about it. And then that is your standard. Of course, it may not be exactly 1 kg, but you know exactly how much it differs from 1 kg. Now, apparently, these gentlemen, they call themselves the Avogadro project. They're counting atoms, right? So what has now happened is, Avogadro's number has also been fixed, okay? No time to measure it. But they fixed a value which is consistent with the other definition of the kilogram, okay? So both seem to be, so that's the story of the kilogram, which I've told you maybe in more detail than the other topics. But as I said, this is where there's a lot of very interesting physics still ahead of you, but I've given you a glimpse, okay? That's what the sphere looks like, actually. Pretty beautiful. Okay, so now we come to dimensions, and we'll also see how we are doing for time. Okay, started at 2 and 3:15, right? But some time for discussion shortly. Okay. So I really got hooked onto dimensions by the first page of a book called Approximation Methods in Quantum Mechanics. I hope you have not read that book, because then you will not be impressed by this. So this is a right-angle triangle, and it has some angle alpha. Of course, this guy is pi by 2 minus alpha. Alpha is dimensionless. The radians, the ratio of some things. So the area of the triangle, if C is the hypotenuse, or H is the hypotenuse, is H squared times some function of alpha. Actually, you know the function, right? This is H sine alpha, this is H cos alpha. Multiply, you can take one as the base and other as the altitude, because this is 90 degrees. So this F alpha is actually half of sine alpha cos alpha, but we don't need to know that. Okay? So then, you drop this perpendicular. So for this triangle, all triangles have alpha, that you can check. I mean, the big one, this one, and this one all have alpha. But their hypotenuse, this is the hypotenuse here, and this is the hypotenuse here. So basically, you get F alpha into A squared is equal to F alpha into B squared plus F alpha into C squared. So if you can get Pythagoras theorem from dimensional analysis, surely there must be something to it, right? So anyway, as I said, this was my introduction. Now, so let's just take the case of length dimensions. Let's not bring in mass, time, charge, any of those things. So one very commercial way of thinking of dimensions is, suppose I go to a shop and say, okay, give me a string. He says, okay, of this much. And he says, okay, it'll cost you 10 rupees. Then I double it. And assuming that it's being fair and you're being charged account by the total mass there or something, he'll say double, okay? So in that sense, a string is one-dimensional because its cost varies as L to the power of 1. Cost or mass or whatever you like. If I say a handkerchief, and then I say, okay, give me this, he'd better charge me 4 times, right? And finally, and this is the one that actually people find not very intuitive, that I think this, I really became aware of this the first time I went to a function in Shantiniketan. And they gave me something called a Rajbhog, which was a rasgulla which roughly double the diameter of a normal rasgulla. It took me a while to realize that I was eating 8 rasgullas, okay? So the dimension of a rasgulla is 3, okay? But what's interesting is that there are objects where this dimension is neither 1 or nor 2 nor 3, but can be even fractional, okay? So, so there is So there's a particular kind of carpet. Okay, this is too small. Which is named after the Polish mathematician Sierpinski. So it's made out of equilateral triangles. So you start with a small equilateral triangle, okay? And then you create a Sierpinski carpet of double the size, right? The original had this size. Now you have doubled the size, right? But the actual mass has gone up by what factor? Because you left this hole here. Huh? The side has become doubled, but the mass has gone up by 3. Okay? Then at the next stage, the same object is replicated, right? So again, you have doubled your size, and the mass has gone up by a factor of 3. So now if you go to a shop which sells Sierpinski carpets, of course, he has to start from some size, right? But what you buy need not be this triangle. You could buy bigger ones. And you say, give me a Sierpinski carpet of this much. And he says, okay, 1,000 rupees. And then you say, give me this much. How much should he charge you? 3,000. So now tell me, according to the same logic that we had, what is the dimension of the Sierpinski carpet? Okay, I claim the mass is L to the power of something. Okay. Some dimension where, okay, so if I, suppose I say some k times L to the power of d, and then 3m is k into 2l to the power of d, right? I doubled the length of the carpet and I had to pay 3 times. So now can you tell me what's d? Three by 2 power d equals 1. I think if you divide these equations, so d is what it's log 3 over log 2. To what base? Yes, I was waiting for someone to say any base, right? Because when I took logs, the equation works for any base, because if you change the base, both log 3 and log 2 change by the same time. I was brought up on tables of logarithms, so the few people in this room who may know that log 3 is 0.4772 and log 2 is 0.3010, and if you divide them, you get, I don't know, 5 by 3 or something like that. So that's the dimension of the Sierpinski carpet. So I will give you one more thing, which is more like a piece of jewelry, and I'll leave you to compute its dimension. Let's see. This time I'll make it from the top down. So first, you do something like this. Then you remove. This is something with a notch, right? These are all equilateral triangles, by the way. Then you do this. Then you do this. Then you do this. Now you can repeat, right? Every one of these. At any stage, you have links of the same length, right? And as you subdivide, each link is replaced by 4 links, though its length actually goes down by 3. I don't know whether, I'm no expert on either carpets or jewelry, but Just for fun, you compute the dimension then. Let me know. So, these are geometrical examples of fractional dimensions. There are natural examples. So the great but maybe I will give a little time for the great advocate of fractional dimension was a man called so in his book, he has an interesting section called What is the Coastline of England? Okay. I mean, you've already more than once encountered this interesting relationship between France and England, right? So here is a French guy having taking England as an example. And he actually makes an interesting case that, okay, you look at, so maybe you take a map and you take something like a divider. Now, a divider is something that we used to carry to school. It's a lethal object with two sharp points. How many of you have used compass and divider? Okay, good. So you take the divider, separate it by some unit and keep going, right? Count. Just like counting squares to get the area of something. Except you better check that if I make the divider half, the number should go up by a factor of 2 if this boundary is an object with dimension 1. Right? If it's like a string. But he takes maps and shows you that it's not 1. Because what you think looks like this, you blow up the picture and yes, it goes from here to here, but it actually does this. So okay, you look at this, then it does that. So till you get down to probably a grain of sand or something. Right? So the coastline of England is not that well defined as you might think. So it's a natural object. Clouds, you should catch Rama Govindarajan if you want to know more about clouds. They look pretty as if they have some fractional dimension. In this case, I know more about interstellar clouds, not the ones that you see, but the ones that radio astronomers measure. They have a dimension around 2.6. It's been measured by people. So I just thought I'll toss this idea of dimensions being fractional at you. So I've already given you one example of hidden assumptions, the square root of L by G, where you have kind of built in the independence of mass by, even if you put L, G and M, the fact that there's a G there tells you that it's independent of mass. But again, with the same simple pendulum, I'm going to ask you a question. Suppose I take L to infinity. What do you think would happen to the period? I'm sort of confining myself to this area. I think I will still do that. I will. Well, the obvious answer is infinity, right? But see, it's very expensive to build an infinitely high tower and put an infinitely long string. But what do you want? You ultimately want the bob to move in a horizontal path. So let's do that. You make a tube, a horizontal tube, put your ball, well, move it away. And what is the period with which it will oscillate? On Earth, of course. Huh? Okay, I'm going to give away the secret. Here's the Earth. So this is G. And when you move the bob here, this is G. So is there a restoring force? If I displace it by X, right? This is the restoring force, which is G times X by R. Whereas, of course, for the normal pendulum, where you took the Earth to be flat, it was G times X by L. So therefore, the period of this oscillation is square root 2 pi, of course, square root of r over g, the radius of the earth. So what has happened? L went to infinity, but one more length, which we thought was irrelevant, has suddenly entered the problem. By the way, it may be very difficult to build this. Anyone can quickly give me what this number might be? More than an hour, I think. But it's a reasonable. So this is not so much to suggest that one should build such a pendulum, but to tell you that a dimensional argument invariably neglects, so hides certain things which may be relevant. We don't know. So, okay, not for my lecture, right? No, I know. I thought people will start walking out if I tell them I'm going to lecture them for 90 minutes. Yeah, actually it also agrees with the orbital period of a low Earth satellite. And I think that's how Sam got it, maybe. Okay, I'm going to stop with this one. Huh? I think one could keep. Let's look at the drag on a body in a fluid. So here's something, and I'm moving it in a fluid, and even pendulum gets damped because there's a drag. No. So suppose we, okay, let's get rid of all this quantum mechanics. So there's some sphere of radius a moving at the speed v, and all of you have been taught that the drag force is, I mean, perhaps, I don't know when it comes in the syllabus. Something to do with viscosity or, huh? Okay, maybe it's not in the early syllabus. So let me write down that it's a famous formula. It's called Stokes formula. And the only thing I should tell you is don't put an apostrophe here. His name is Stokes, okay? If you want to say he owns the formula, put one more S and put that. Huh? So this is Stokes. So does that ring a bell? People have seen this or not? Okay, this quantity eta was, where do I have it? Oh, I rubbed it off, 6 pi a eta v. Huh? Now, it's historically interesting that the concept of eta was introduced by Newton. It's in fact a fluid which obeys this law is called a Newtonian fluid. That is, we have two layers moving at some relative velocity. There is a force between the layers, a frictional force, which is of course proportional to the area of contact and proportional to the velocity gradient. That is how fast the velocity changes from one layer to another. And eta measures that. But Newton himself gave a different formula for the drag. This is Stokes is much later than Newton. Newton gave a formula which is intuitively quite nice. He said, okay, here's the sphere. Maybe it's moving at the speed v. I will sit on the sphere and then the whole fluid will appear to, of course it has to avoid this, right? But roughly speaking, there is some area which is some pi a squared. And the amount of fluid flowing into that area is rho times v. This is the mass, right? Again, same argument that v, the same argument we used even for the electrons in the Hall thing. That there's something called a current. Current multiplied by area will give the total flow. Density times velocity. But this is only the mass flowing in. What you really want to know to get the force is the momentum being given to the sphere. So put one more v, okay? So this is the kind of formula. Of course, this is kind of dimensional analysis. So there could be other factors in front. Now here we have two formulae for the drag on a sphere. Now if you look carefully, this one doesn't contain the density. This one doesn't contain the viscosity, okay? So now it looks like we have four quantities. With four quantities, you will not get a unique answer from dimensional analysis, right? Normally when you say, I have something, and then I want to express it as m to the power of x, L to the power of y. You need 3 equations to solve for x, y, z. You have 4, you will get multiple solutions. So you can get this, you can get this, you can get any ratio in between. So you need more physics. Turns out that this is valid when it's moving extremely slowly. Stokes. This is valid when it's moving much more rapidly. Now, there is more deep physics in this, right? If you read, in fact, Feynman calls this formula the flow of dry water. Dry because you're neglecting viscosity. The Feynman lectures which Sam mentioned. So I thought I would leave you with this remark that there are cases where dimensional analysis will not give you the final answer because you have too many quantities, but you could still, if these have the same dimension, you could divide them, right? And if you divide them, you will get something like rho times A times V divided by eta. This is dimensionless. So now you say the drag is, you can give either formula, but you also have a dimensionless number, and you could have any function of that dimensionless number, just like we had sine alpha, cos alpha for the triangle, right? So this is, by the way, called Reynolds number after the gentleman who introduced it. So at low Reynolds number, this is true. High Reynolds number, this is true. But I wanted to just leave you with this little lesson that even when dimensional analysis doesn't give you the final answer, you construct dimensionless quantities, and the experimenter can then investigate how things depend on these quantities. So I think I'll stop here and we can maybe follow up on anything that you would like. And as I said, all these, okay, so what it's worth, let me see what is that in mind. Oh, okay, if no one comes up, oh no, at 3:15 I should definitely stop. But there is an interesting case where you get dimension 0. I'll just leave it at that. That's it. Yeah, that's the only topic which I left out, dimension 0. Okay, yeah, I'll do it. You've seen swimming pools, right? So swimming pools have diving boards. And they have a 5-meter board, 3-meter board, 5-meter board, 10-meter board, so on. And if you look at the depth of the pool, typically it is 10 feet. Would you agree? So let me justify this based on dimensional analysis. We'll use Newton's formula because the Reynolds number is. So you are now coming in and you have a kinetic energy of mv squared. And you'd better not have any kinetic energy by the time you reach the bottom of the pool, right? So therefore, this much of kinetic energy should be accounted for by the drag force acting into the depth of the pool, right? And the drag force is proportional to rho times a squared times v squared, right? That we just said, density into area, cross-sectional area, into the square of velocity. In fact, even this m I can replace by your density, and your density is the same as water, pretty much. Otherwise, you couldn't swim very easily. Into the length, into the area. So if you cancel everything, you will conclude that the depth of the pool should be your length. Right? Which is a fixed number, your length. So no matter what height you dive from, you should stop, well, maybe not your length, it is 2 meters. I mean, if you're one of these super swimmers, maybe 4 meters, and it's true. So there's some truth in this argument, but it cannot be the whole truth. Obviously, if you enter the water with a higher speed, you will first slow down to a lower speed, and then you lose your energy. So it cannot be that the depth is independent of the initial velocity. simple dimensional argument tells you that it is uh, velocity to the power of 0. Velocity cancels. As in the rest of this lecture, I've cheated you. Okay? The correct thing to do is to write a differential equation. The rate of change of this with respect to distance, some z, is proportional to v squared. So now you get log of v squared going as z. And that's the correct answer. So you keep increasing the velocity, the depth will increase, but not as any power of this distance. And if you do the whole thing properly, you will probably get a formula like the z over your length is log of v squared over, but by the way, this had better be dimensionless, like the tip formula which I gave you. So this I will leave to you as an exercise. So that is a case of dimension 0, where something appears to be independent, and then immediately your ear should prick up and say there's a logarithm here. I mean, one silly argument for saying why, suppose I differentiate x to the power of n, or suppose I integrate x to the power of n, I get x to the power of n plus 1, right? So let me integrate x to the minus 1. That should give x to the power of 0, but it doesn't, it gives log x. So whenever you get dimension 0, most likely it's log. I don't want to advertise old lectures that I gave decades ago, but I once gave an entire lecture on this called Some Logarithms That I Have Known. But anyway, you keep encountering logarithms in such problems. So I hope that's enough about dimension 0. And actually we are stepping out also, no? So why not?